to join those ones as well. But now to continue, we're going to present to you the cool stuff that is going to make all your life easier. And Suresh from Georgia Tech is coming here to present you an introduction about that. So thank you, Suresh, is all yours.
Yeah. Thank you, Rafael. Yeah, good morning, everyone. So this is a new project. It's a multidisciplinary collaboration between Ahmad and Rafael's group and our group at Georgia Tech. And then we have other science domains as well. So we'll not introduce I'll keep it relevant to the context here and not talk about the whole project that has the project also has other science domains here, more neuroscience and other domains as well. So we'll keep it focused on the molecular dynamics. So as you can see here, it's a very interdisciplinary team, and so we'll kind of explain why and what we are doing together. So what essentially for this context, what we are doing is we are kind of all within this large project, and also as a reflection of our group at Georgia Tech also is, so we are very interdisciplinary in nature. We are trying to enable science, particularly computational science, in a very how can we streamline that and how can we scale that up, and using cyber infrastructure. When we say cyber infrastructure, that all the remote high performance computing machines, the data storages, how can we make various applications easier and so on. And then we do a lot of in the open source area. And today for this workshop, at least this time, we are not going to talk about some of the AI work because we don't have that working yet, but like this is also an area where we are increasingly looking collectively for molecular dynamics as well, in collaboration with Ahmad and Rafael's group and what we can do. So largely, I'll open up to a little bit of a discussion and want to get feedback from all of you before we get into some hands-on and demonstration. But largely, why we are working together, and what at least motivated Ahmad and Rafael to work with us on this is the idea here is how can we create end-to-end cyber infrastructure? Can we if we really look at this is not this is a digression from the rest of the week what you have seen, but with a very broad and ambitious goal on how can we accelerate science? And to that extent, if we break that down, what are you doing and how you are doing? So obviously to do that, we need to slowly build this up. This project is a 5-year NSF funded project. We are in year 2. So we hope to evolve, and if you are following a project and the progress, we hope to have go from bottom up a lot. So what we are trying to do is if we take a look at these computations, and which is what what you will see in the demo today and some hands-on in the afternoon is up until the third block from the bottom. So how can we first start out with, where do you run all these large simulations and how can we optimize them? How can we make it easier? Then think about, how do you distribute all your data? It's on your local laptop, maybe on your lab server. When you run larger and larger simulations, they get fragmented into other machines. How can we help you analyze all of them in a little bit more seamless way? And then that's where, and then what we kind of realize is many of you have VMDs now on your local laptop, but when you have data sets from a single simulation, you can analyze that. But many times you will have simulations doing larger systems on a remote machine itself. And those grow in sizes, and then you are doing replicas and replica exchanges, and then more and more as you scale up, you will have larger simulations. So it's not always possible to bring everything to your laptop and analyze it. Can you open up VMD on the remote machine, but in a very seamless way without having you worry about technical details, which is what Diego will shortly show that demonstration. How can you do that with certain simulations? And then, so what we hope, that way we are right now in year 2 of the project. How can we show you that seamless one? But we are very actively interested in, please feel free to talk to us at lunch or in the afternoon. What we are doing this in other areas, but what we in the outer years, what we want to do is how can we accelerate MD in some of the AI approaches, and or even bolder vision, which we are very speculative at this point. What we are not there at is how can we really, if you have a scientific question you are pondering, how can we build systems? Can you go from a question to a computational experiment construction and scalably, run those in a very seamless way, and then maybe learn from that and help you draw insight from your computational experiment? How can we build that kind of a closed loop system is kind of an aspirational goal we have. Again, these are like, a little bit of a research topics, like, we'll be happy to talk. But the focus today, like, is what we want to show you is what we have built so far, like, and how can you optimize some of these computational workflows? So some of the things what you've been doing. So again, from this simple step, like, if you just like look at it from a very coarse view, we take a look at this as three building blocks, right? Three steps, like, and when you're kind of preparing your structures, like, and then you're running these large MD simulations, and then you need to analyze those simulations. And then, but what I think when we are writing this proposal, what motivated is, we realized that that's not a simple linear process. And as with any other scientific question, what you do a lot of iterations, and you're kind of I mean, this is a general for any science, like, if you look at it, you're doing a lot of iterations, course corrections, like, and then, like, scaling up. And then this like process of doing this, all of these steps, you have to use local machines and scalable machines, and then like things get federated and so on. So over the years, what we have seen is a lot of cyber infrastructure efforts have focused on making a little bit of simulation steps easier. How can we run, like, if you see now and then, maybe you're using HPC resources on the national machines or on your institution, you see some gateways and other easier ways of browser-based access on those interfaces pop up. So those are good, but what we see is gets missing, which is what we are trying to address, and we want to have you do some hands-on exercises today is, many a times, like, most of the time where you're spending is on your local laptop. And Rafael was saying how big of a workstation his group has. So when you are like, focusing overly on these large HPC machines, which are getting bigger and bigger, we are sometimes ignoring, like, the local capacity what you have, and that's where you are spending time on this. So the key mission, what we kind of were looking from CyberShuttle perspective is, how can we really integrate end-to-end, what we call the continuum one? How can we create a cyber infrastructure continuum, starting with your local laptop, and you do as much as you're possible locally with your local tools, but at the same time, make the seamless migration to the remote machines, and without, as a user, you have to learn the technologies and go back and forth is kind of like the tooling what we are trying to develop. So a large portion of that will start with obviously the data distribution. So once, a portion, these are the details under the hood you will not see, but you will see some of the things what we are working today when you see the demo and some hands-on portions is, we are trying to look at everything the data is as a distributed file system, starting from your local laptop. Can VMD really make not just only work with local data, but a distributed virtual file system with securities dealt with, data moving the data seamlessly, and all those things, like, and then have a simple metadata, virtual metadata layer where you can see all your research in a single place, the metadata part. The physical data may be spread out, but how can you create a virtual view is what we are trying to look. So, and then when you combine that, like, what is, okay, how do you have your local environment with a virtual view, and how can CyberShuttle enable to move between them, like, as a central place? CyberShuttle can also capture your research workflows, like, as you are doing lots of simulation for a given project. So how can you really capture all of those, and then integrate that and help you search across them, reproduce them, like, and publish the metadata associated. Like, one of the things what we will be looking next will be is into the VMD steps also, like, lots of things. John Stone presented that, and previously, early in the project, John Stone pointed us to the logs, how VMD detailedly logs each steps, so that you can, like the big NAMD simulation, you could also checkpoint restart the VMD operations. Like, these are human operations. So one of the things what we will look into in the very near future will be, how can we capture those steps also if you're doing on the VMD steps, and then record them and reproduce them, maybe up until the third step, and then come back from the fourth step. And as you can see, like, so many, options are available, right? What kind of capturing we can do and reproduce them, and then migrate them. You did some half of your VM steps on a VMD on one machine. Can you take that and start from those steps on a different machine, or share them and have your colleagues reproduce them, and all of those will be of interest, what we'll be looking. But these are, again, something we've been understanding that these might make your research process more effective. But before we switch to the demos, we'd like to hear from you, from your day-to-day research experiences. Help us with this. If you do X, Y, Z, this will help our research process more streamlined. And from what you have seen this week or in general, we would like to get that observations. And then when you will see these demonstrations today and then the hands-on, you will see the two options. I'd like to clarify why you'll see a web portal and a local app. The point is, like, most of the time when you are doing heavy intensive work, when you're doing VMD, you would need to have a locally installed VMD, or you'll increasingly probably you'll be using Jupyter tools, or sometimes you'll be running NAMD simulations also to a smaller scale on your local machine. And then you will have all of those done, and we would like to integrate that. But often when you're not running the actively simulations local machines, you would like to get a quick snapshot on what's going on. You don't have to have a local app installed. You can log into your web browser. If you have an NAMD, VMD, all the NAMD inputs prepared, already uploaded directly on the browser without no installation required. Just submit to various machines and watch progress and so on. They could do most of the stuff on a web browser, but the local app, when you install, it has a little bit of a distinct functionality of integrating with your local application. Right now, it is VMD and Jupyter, but increasingly, maybe we might see more and more other apps also integrated. So again, what we were working on in the proposal is an overwhelming busy figure, but just wanted to say, share what we were really what the vision is. We are trying to go from this end to end. If you really look at the first step again, if you're going from grabbing data from PDB, and then you're working with PMD on all those steps of structure preparation and setting up your solvates, and then you have your simulation input, and then you run the big MD simulations, and then you need to analyze your trajectories. And then what we see, the point of this figure B, the row B there is, some may be very UI driven, some may be scripted many a times, and sometimes you might be integrating a lot of other tools Charm GUI or bringing in, and VMD you might be using for analyze, or increasingly you might be writing a lot of Python scripts so to do that. So what we envision the way CyberShuttle should facilitate is, we should take whatever your comfortable approach is no one size fits all, but we should let you do your work, but help you with the task, okay, don't worry about the security, don't worry about how to construct a remote job, do not worry about where the data is, just program it as if it's virtual, and then we will take care of it. And then that's spread between multiple HPC machines or a local app and so on. So that's where what we are looking. So with this, what we feel again, our view for this award is we will develop a tool where it will really create a seamless continuum. You will start from your local laptop as if you will keep there, and then and the interface could be a scripted or a Jupyter notebook, or it's you're writing your own code, or user interfaces, and then and then maybe you're slowly plugging into workflows where they may be on your local infrastructure, on a campus level clusters, on a national infrastructure, or the storages could be anywhere. But how can we create this seamless continuum is what we are really looking for. So before I turn it to Diego to do this demo, I'll also put this link. You can start looking at this. You should be able to log in and then use your institutional login, and then start playing around. But we will give you a hands-on guided step by step. So hopefully it will be easy to remember, md.cybershuttle.org. So let me pause here and get any, I know it's a little bit of a phase shift from what you were used to the rest of the week. Anything resonates with you guys, or would like to give feedback for our team early on? And if any of this where you find will be more productive, will make your work more productive, or other things. Yeah.
I just have a question. If this integrates with like if our university has a local cluster or if it's only the access supercomputers.
It is a local cluster. Any cluster which has a scheduler. So we do not have a mechanism right now. If we do not have a scheduler, how do you manage job? But any cluster which has a scheduler built in, right now can like do that. In the near future, we might like have other PyTorch with other non-scheduler interfaces. But right now, as it stands today, what you can right away do will be, if you have a cluster with a scheduler, like and if you have a local account, Diego's demo might already cover that, or it will be happy to do a hands-on. Today afternoon, we can make sure you can add your cluster details. There are some nuances, like so all the time, like security. If you have a DO enabled, if your cluster needs VPN, we may have to work through it. But if the cluster is open to work like from anywhere, like that will be very straightforward. You should be able to do it today. The extra security steps will take a little bit extra to work with and to understand what security policies they are and how to work with them. Yeah. Any other questions in general, like, again, need not be about computations on like, again, our goal here is between the Ahmad's team and like, us, we have we are very interested in making like, the aspects of like your research workflow more seamless. So we would like to understand what they are.
So can you take some inputs from Amber?
So Sudhakar, do you want to answer that? So because yeah, there are multiple things, but let Sudhakar answer that.
Yeah, so I think for now, this is more focused on NAMD. But as you see, it is not a NAMD.CyberShuttle, right? So eventually we want to add all molecular dynamics codes and simulations and the analysis tools eventually. For now, for this week, or maybe for this month, it will still be just NAMD. But we know how to add applications. You already see that even in this MD.CyberShuttle, we have a quick fold, which is an AlphaFold based extraction of structures from AlphaFold based on a sequence. We can add multiple applications here. Though only the NAMD and AlphaFold are active. Though he sees a lot more things, but not all of them will be active for you guys. See, the infrastructure is very generic. That means that even if a particular molecular dynamics application is not there, that doesn't mean that it will not be there forever, right? You can request one and it can be put there. And you should be able to access not only the application, but also some resources, where the application would be executed.
Yeah.
And also you should be able to add your own resources, like your campus clusters, or if you have allocation and access, or you should be able to put it and use that through this.
Yeah. So I'd like to just put a plug to the other gateway Sudhakar operates as a PI. Called Science and Engineering Gate. So in the Science and Engineering Gate, what Sudhakar has been doing is for the last two decades is he's been trying to make quite a lot of computational chemistry code, like Gaussian games and like an MD code that includes the LAMPS and Amber as well and others. So this, if you are interested in using them like on the national machines, you could do that today. This has Amber, but like what I would like to clarify is, with CyberShuttle, we have a distinct goal. Like what we are trying to do is these ones, you can just like you're on your own in some sense of preparing your inputs and uploading. So if I go to Amber here, so what you will see is it will expect you to create all these input files in some ways and then upload it. So this is what most of these gateways are. But what we are trying to do in CyberShuttle, which as I was trying to say here is, so what we would like to invest more into the end-to-end part. So in the future, what is that Amber input generation and what is the overlapping here? That's the ones we need to invest more time. But right now, if you know already how to run Amber and if you know how to construct input files and upload them, yeah, there are interfaces like cgrid.org, you should be able to use it. But end-to-end Amber support in my md.cybershuttle probably is not there, but in the future, again, these are all. The way we look at this is these will be very community driven. The more you as users are asking and requesting, we will try to work those in, and that's the way we plan to work on this. Other questions?
I think one challenge for me when I have a lot of simulations and all of the features and everything is the data storage after and how to organize that. And maybe if you write programs that are going to find the data files, do you think that in the future this
Yeah.
program would develop some type of like MD specific database?
So it's actually, that's coming in very near in the next 6 months. So that's our next big step. Like, here we've been actually talking with Andrew last night also on this. So what we are trying to do is we focused on for this release on how to make the computations easier, how to plug in from the VMD. The immediate next step, now that it's working, what we need to do is, okay, how do we capture those NAMD outputs, organize them, and lots of those, and then help them search across them, and so on. So there are already some toolkits like what we do. So we use the CClib parser, which also happen to parse the NAMD input and output. So how good they are, we need to look at them, and we are kind of investing that, okay, what it takes to understand NAMD, the trajectories in a good way, and then can we put them in your database, and then have you search over them. So this should be hopefully by, as Raphael said, there might be a workshop end of the year. By that workshop, we might have that capability. Any other questions?
We're also writing a proposal for some to enable some kind of distributed storage like setting. See, the storage is always a problem, right? I mean, now you have a terabyte or a petabyte of storage. In 4 years, it will be 5 petabytes. Where do you go? So we have to have some kind of a sustainable pathway to make sure that your data is, captured, But if you cannot store them forever, you can throw away the old simulations and then rerun them. See, we expect that in 10 years, let us say, these programs and the systems will be, so advanced that you can probably rerun some of your, 100 nanosecond calculations in a day. Instead of storing them and discovering them and finding them, retrieving them, it may take a day also. So there is a balance in terms of whether you want to store the data or throw it away and recompute it. So, but then for some time you need to store it, maybe for a few years, I would say 5 years. After that, maybe, the data is probably garbage. Anyway, if you want to rerun it with maybe new force speed.
New force speed on that day.
Yeah, so again, well, if there are more questions, again, I was just playing the video which Diogo will demonstrate hands-on step by step, and then just want to show you that there are instructions we'll be able to have you take with you and hopefully run. Again, this is a new release, so we just got it. As you probably all understand, anytime you make a new software, there will be bugs, and we hope you'll be patient with us, but we're actively working on this, and then we might run into some bumps with network because we are learning, some ports get blocked and so on. So we will have you all try this out, but there may be bumps, and then we're just wanted to assure that we're actively working with those as well. So again, there are no questions. We can have you switch over.
Thanks, Suraj, for the presentation. But that's about using it here in the room, is because we noticed yesterday that Edinburgh blocks some of the.
And I'm not on
blocks
Zoom.
some of the meeting.
I need to go to the Zoom, right?
You're not gonna have that problem in your institution with your login.
Yeah.
Yes, so Vladi,
Connect.
we can do it in your computer
So
Yeah.
instead.
There's a lot of stuff.
Yeah. We can do it in his computer, as long as you connect to Zoom. So while we set up the things, something that is new, so EduRun was blocking it yesterday. And today, if you're from Auburn, you may not be able to use it, because now Auburn is blocking it. So if you have an Auburn issued computer, you won't be able to CyberShuttle today. Maybe in 3 days. Yeah.
Mute.
Oh,
How come you
multiple
don't have
mics?
this set up and share the desktop properly?
It's just share it. It's just,
Okay, all you need to do is share your desktop, right?
well, Zoom, yeah. Whatever you see on that screen there is what Zoom is showing.
I'll share my whole desktop.
Okay.
Good.
Ah, it's over there,
Yeah, that's Zoom.
but it's not being shared.
No, he didn't plug the cable yet.
You plug the,
Oh,
yes, plug the cable. So we want to show now an example of you using the
So,
CyberShuttle local agent, not the website, it's the rest of the show. So we have multiple options, so 3 options of use CyberShuttle.
maybe we can
Oh, yeah,
show
yeah.
both.
Oh, I didn't make it.
Let me put the microphone, so
You take the microphone.
You're the one that is not like.
that good now? It's on,
No, that's not the one.
all right. Ah, it's hidden. Okay. How about now? Yeah, yes? Oh.
I don't know if I'm hearing
But it sounded. Oh, now it's. Now it's better?
Yeah.
Okay, great. So there are 3 ways for you to run CyberShuttle: submit simulations and see the results. First one is the gateway. That is just a website that Suresh just showed. The second one,
show it
you can
again.
submit and view the results from PMD, but that's still buggy. It only works well for Windows and Linux. So Mac OS not working because Apple blocks stuff. And the cross-platform solution is the CyberShuttle local agent. So the first thing we're going to do today is to show you how to download the CyberShuttle local agent. All you need to do is just like the video that Iroma was showing. Go to md.cybershuttle.org, and then you can go there, up there, download for your platform.
Yeah, so there is a client in the bottom of this page for Windows and Mac, which I don't see one for
On the
Linux.
top of the page, you see you have 3 options. So
Oh, there are
if
3.
you click on download, you have the option to download for Linux, right on the top.
Ah, okay. Yeah, there also.
Yeah, we don't have one for Windows ARM right now, right? Okay, so once you download and install the agent, we want to show you how to create one simulation. So y'all know how to create like input files for an MD. So run your simulation either manually or using QuickMD. So for this example, we are making it available one test for you to use, or you can use your own test. So,
So I think,
can
yeah,
you-
most of you have been given logins on this, the md.cybershuttle.org. I mean, I saw one from Vanderbilt that has some problem, looks like with their user ID. So if you have a problem like that, I don't know who that person is. I can find out who it is. This is from some Vanderbilt University login. They can create, I think, their own login, and then probably use that. Oh, in CyberShuttle client, I think now we have only institutional logins. So for the Vanderbilt person, they need to talk to their, internal support for the CI logon and enable that CI logon to work properly. So I think there is some issue.
If all goes wrong, you can log in from PMD or from the gateway.
Yeah,
So you can log in with your Google account, GitHub, right? Orchid. There are
Right.
plenty,
Yeah, so
8,000 options, right?
yeah, so the
Right.
Vanderbilt one is not working. Yeah, try to use Orchid or Google or one of those. Yeah, that should work. Okay.
Right.
And okay, so this is the client that I just opened. Okay, after downloading from this set, and I'm going to try and log in myself. So there is a list here. I can search for my institution. Though I'm at Georgia Tech, I'm using my Indiana University ID, which is my previous ID at this point, which I have. I mean, I already have access to this gateway using that login. Bear with me.
How do you remember that?
Oh, wow. It's a big secret.
Yeah, he was cheating on the phone.
Yeah, this is my duo challenge. Okay, so now it authenticated. Okay, I'm logged in and I see some experiments here. So, so I don't know how much time we have for this. So maybe, assume that this is a demo. I mean, let us say we'll do hands-on leisurely in the afternoon. Okay, just follow what we are doing for now. And you'll be doing similar things in just a short while. Okay, next. So let me say what is that you're seeing here, or you can say that too. So this screen starts with a list of past experiments that we have submitted, or in this case, I'm an administrator on this gateway. I see everybody's jobs. Okay, for example, Suresh's job is right on top. Okay, Diago's is next one, Aroma, and so on and so forth. So there are many users in this gateway, like all of you guys who just joined, and all jobs are available to the administrator. But if you log in successfully into this client, you may not see all these things. You may see only your jobs or some of the experiments that either myself or Diago have run and shared with all you guys. So this system also enables people to share, these experiments and inputs and outputs with your friends and PIs and colleagues and so on. So that way, multiple people can look at these results together. So there is some kind of a search criteria here. So here, we are searching based on an application. Okay, but you can search based on other attributes like a username. Okay, so maybe I will pick Diago's username and we'll try this. For now, instead of application, I say username, and then I add not type it. B 0054 at Auburn. And if I click that, so the list has changed and it is showing only Diago's
You show only the completed ones. You
Okay.
can also search
Yeah,
by
so and also we can
function
say
state.
that we can show only the completed ones. Okay, so these are all completed ones, but some of them are VMD kind of jobs, and there's no point. So for those jobs that have some data or NAMD runs, okay, for NAMD application, we have these two buttons, a VMD and a Jupyter. This VMD is an interface to the VMD application running remotely. Okay.
On the supercomputer.
Yeah, on the supercomputer. So before I go there, so this also says the resource where this NAMD was executed. Okay, so for example, these two, we executed them on Expanse. It's actually Diago. So if I select this, take a minute to tell me more about what this experiment was, some experiment ID. So there is a description. I mean, he didn't add a description, but one can do that. And then some, job ID that was given by the local scheduler. This is a Slurm scheduler on Expanse at San Diego Supercomputer. And, so the 0 MB is not 0 MB really. I mean, I think by default, it gets based on the number of CPUs that were selected. Like for each CPU, I think we get a 2 gigabytes of memory. So this should have gotten at least 40 gigabytes of memory allocated. So it was running on a partition called GPU shared, and so on and so forth. So we'll see how to set up these things in a moment. But this is one of the past runs. Okay. And So maybe I should try and launch a VMD.
Let's first send the job.
Okay.
And then we'll see the results of this one because we don't want to wait 2 hours to see the.
Okay,
the
so
outputs.
maybe, okay, so there is a button here on top called Create NAMD Experiment. I'll click on that. So this will give you this job submission interface. Okay, so there is some kind of experiment name that I think is pre-populated with the current date and time here. You can modify this. For example, I can give some, what is that input?
Auburn-Workshop demo
Okay.
2. The one's there.
Workshop demo 2. Maybe we can also describe. So you can say add description. We can describe it. Do you know what that system is? Briefly, Diego.
You can write anything. It's
I can write anything. I'm trying to write something more meaningful.
They call it full experiment.
Full experiment.
Yeah.
Okay.
So the system he's doing, I hope, is the one that I showed yesterday from the science paper. It's just adhesion with a peptide complex with it, and it does seared MD simulation, like a short one.
Yeah.
Just
So
run during 2
so
hours.
if you add this description, this goes into some kind of a metadata for the experiment. Eventually, you can search on the metadata as well later. So that's a potential. But of course, it requires some kind of a discipline to add this metadata and so on and so forth, upfront. So, and then, we have these projects, maybe just quickly, there is a default project. Probably most of you will have only a default project available. Oh, that's all. It looks like I can see from here. That's good. So there is no choice. I mean, I used to have choice, but now they have removed it. Yeah.
So if you're an organized person, you might have different projects. And the way it works, so you go to the gateway, create your projects, and then inside each project, you have an experiment. So that's the hierarchy that we have right now. So you can pick to which project that experiment belongs, and you use the description to keep track of it.
Okay, yeah, just to illustrate what has been said here. Okay, I am already logged in. So here in workspace, we have what are called these projects. Okay, only default project is available. So let us say if I add a new project, let's say demo. Okay, I can say Auburn Workshop demo. So now this demo project is available. Let's see if it is available on my local client. Okay, I need to refresh this, I think, somehow before maybe back to the experiments. Let's say. Okay, now let us say create NAMD. Oh, now I see demo. You see that? Yeah, magically the demo appeared. So, I created this project ID on the gateway in the portal, web portal, but the information is shared between local clients and the portal. So they're talking to the same data in the back. Okay, anyway, so you can create these projects, and then you can create experiments under this project, like your NAMD. Okay, yeah, continue. Yeah.
Okay, so now you go to configure your application. So what kind of resource do you want to use? So you're using a project, then you're gonna run NAMD. So for this application, so you gotta choose if you want to run a CPU run or a GPU run. We recommend you to use a GPU with a new super fast NAMD resident code. But depending on the application, you might want to choose the CPU code. And then you can continue a previous run as long as you provide the input files that you're gonna put right away. And then you give all the files you need to run your NAMD simulation. So starting from the configuration file.
Yeah, so for now, I think, maybe for the first run, you don't have any information about a previous run, so you don't want to check that. But if you had some run previously, and let us say, it stopped somewhere, sometimes you may have to restart after a certain length of the, simulation. So then you can actually set a previous job ID and restart from where the previous job number. So that's what this, previous run is about.
So as we explained, can you just upload the file? So the configuration file is the one that tells Nancy what to do with your simulation. It also contains the paths to the input files that you're giving it. Okay, so we prepared one example for you to use later, so don't use it now. And
Okay,
it's called CyberShuttle tutorial. If you can find it, I can show you the link right now.
maybe I should download it and.
Yeah,
then
go download. So go to your browser and
Okay,
type,
go to my browser,
yeah, so
documentation, is it here?
no, just type on the address. I'll give you right now.
Uh-huh,
It's aube.ie
ub dot
.ie.
I,
Yes, E
IE, uh-huh,
/CyberShuttle
cyber,
underline example.
example,
Oh, not slash.
oh, underline,
Underscore. Yes,
underscore, yeah.
Example, and Obi has you put a point in here. Just remove the point.
Extra point.
Yeah. Y'all can access this file if you want.
Okay,
So the recommendation is to download everything into your desktop or download the folder.
okay, so there is a download here. I can download the whole thing?
Yes, download the whole thing and extract the file.
Okay, so it is downloading as a zip archive. Okay, now I unzip it. So it created something in my downloads.
All right, so the first thing you need to upload to CyberShuttle is the configuration file. So there's a configuration file called poll.conf.
Let me go back to the client.
Yeah,
So
go to the
it is
client.
already in download.
Yeah, and while it's uploading, as I mentioned, it's a steered MD simulation. So there's the configuration file. It is pre-equilibrated. So the general recommendation is
Okay, pull.conf. Okay, so
yes,
that is the
set
file.
up your system, run the equilibration on your local workstation to see if everything is going well. Your system is equilibrated, then you send it to supercomputer. That's a common practice that we have everywhere. Once it's
Cool.
stable, equilibrated, then
Did
you
it
run
remove it?
production on the super resource, right?
User file. Pull.conf,
Code.conf, yeah.
open.
And in this folder, in the zip file, not only the input files for your simulation, we also added 2 Jupyter notebooks for a simple analysis and 2 TCL scripts, TCL scripts, so you can run interactive analysis using PMD.
Okay, so what I'm just adding one after the other, these what are typically required files. Okay, user file. Maybe I'll select all these parameters.
You can send everything as optional.
Okay.
So one shortcut that we made, so instead of uploading specifically each kind of file, the parameter, the coordinates, structure, so that could allow the shortcut to just upload everything as optional.
Yeah. So yeah, since we are all very lazy or very active,
Yes.
we don't have time to upload one file at a time, right? I mean, who has time? So now I'll say, okay, I'll copy from this all the way to
That one.
this one and upload all of it. Says 8 files, and I think it probably has it'll know what those files are. Okay.
How does it recognize them, like extensions or what the contents of them?
So currently these are optional inputs, we don't validate them. So you can put anything in there, and because there are all kinds of files you saw, right? There are tickle scripts there are PDB constraint files, some parameter files. Okay, so the whole thing is being shipped and there is no validation. But for the others, for example, if you say configuration file, it is going to look for a configuration file. And of course, we can explicitly add additional validations. I mean, it has to be like an AMD configuration. We can put some things, some intelligence into some kind of a validation here, so that if it is missing some things, it will say, your file doesn't look like an AMD configuration file. You probably uploaded LAMP's configuration file. So I won't run this. So you don't have to waste time, sitting in the queue after, for 2 days and discover that you accidentally uploaded something. So those validations can be added to these kinds of features. So for there are other parameters also. I mean, these are like file uploads. I mean, you can choose some other parameters where also you can have validations. For example, job ID. instead of the right job ID here for the continuation, you can give some garbage string. It can check whether it is a job ID like string or not, and then it can reject or accept based on that validation. Okay, so now I have chosen all the files. Okay, so I think we're not doing a replication at this
No,
point.
not today.
Yeah. But the idea here is to, if you want to do replicas, you're just plain, copies of the same thing with probably slightly different, random initialization. Then you can run replicas potentially, but you will do that as homework when you go home. Okay, so here is another thing. Okay, can you explain this, Diego?
Yes, so just to complete the replicas. So it's ideal to run multiple replicas to improve the sampling of the system, but we will enable other advanced protocols that require replicas, just like replica exchange or umbrella sampling. So that is like in the future, we're going to add more protocols to the gateway instead of you writing the inputs. So the other thing about the allocation is that today you can use the default allocation, which is we ask it expense or delta for time using the supercomputer. But you won't have a lot of time to use that. So you can add your own allocation. So if you have an access account of a project that was approved, you just configure on the gateway, you can configure your own allocation and run like your super big project.
Yeah, so I think we won't demo that, adding that, your own allocation right now. We can look at it this afternoon. Okay? Yeah,
So once you're done
let's say-
selecting the allocation,
It doesn't have time, like, you know, or
he will press also.
No, what's happening? Do you mind also showing people how to ask for an allocation access for the small allocation? Because a lot of them don't know it.
Oh, I see,
And
okay.
also access for the small locations, you also know that it's very easy. And by small here, say something that is actually pretty reasonable for you guys.
Yeah.
Unless you're doing very large systems like we are doing, or many replicas that we're doing, the easy allocations you can get there are like one paragraph text about your research and you can get the
How about we show you after we show you the work?
It's there. I just,
Because I think it's important.
this accessci.org will provide you with information about getting your own allocation, fairly easily. We can talk about it, more later.
There are many types of allocation. Some of them, like they tell you, like, oh, we answer you like in 24 hours. Some of the small ones, like tomorrow you have.
Yeah.
Not even like you don't go for a review, external panel, any of that for the small ones.
Yeah, I think now they allow even graduate students to ask for allocation and then they can get it. Okay, so let's go back here.
So the last part is configuring the resource you want to use.
Yeah.
So can you just you choose the supercomputer that you want to use.
But today we are using, so we have reservations on Delta and Expand, but I think we'll use Expand.
Just expands, and then you go into the details of your allocation. So if you are using NAND resident, you can use as many GPUs as available in one machine. So don't go across multiple machines right now, maybe in December. And then you can select how many nodes you want or how many cores you want. We're missing the how many GPUs you want because we're on GPU share. GPU share normally gives you one GPU per job. But if you go to GPU, you have access to the whole machine.
Okay, yeah, so I think by default, you'll get the whole set of GPUs on the GPU now.
As many GPUs as available on that queue, which is 4 for expense. If it's Delta, you can get up to 8. So Delta has more options for GPUs. 4 or 8, right?
How are the replicas when they run separate GPUs or?
Yes, so the way it's set up, each job is being sent, it's on NAND. So it will use whatever resources available, provided what you give here, and you distribute to the resource. The way it's set up, you will use one GPU per replica. So if you just select 4 GPUs, so one node and expands the whole node, you can get up to 4. If you ask for more than 4 replicas, it's going to break. So if you want to use more than 4 replicas in a single job, you have to add more nodes. But if you're running replicas, you can run GPU resident because it's 1 replica per GPU. You can ask like 128 nodes at once, 1 replica per times 4 GPU each. So you do
But
the
yeah,
math.
that you also need to make sure that you have the allocation
As
available.
long as you have the allocation, right?
Yeah.
All right, so once you're done configuring, you can just set, save and launch.
Yeah, so
Okay,
you can
just
change
save
these
launch.
parameters, right? I mean, so instead of, okay, so node count for a GPU shared, I think it is set to 1. I don't think you can change it. Oh,
Yeah.
probably. Okay, so there are some limitations, so I don't know, we can add validations for these things too. So let us say, under GPU shared queue, you can only request only 1 node. I mean, that can be restricted. I thought it is restricted like that, but somehow it doesn't appear
But
here.
it should. And also the number of CPUs, put 10.
Yeah, and also,
It's
yeah,
gonna
so I
block
mean, when I clicked on GPU, change it to 128 cores per node. That is what is available on Expanse. We're not going to abuse it, so we'll just reduce it to 10 cores. The time you can set, there is typically these, okay, so they're all 48-hour, wall time limit queues. So you can go up to 28 minutes, but for now, we'll just stick to 30. And see this physical memory, you can also set amount of memory requested. But, in most of these shared systems, the amount of memory requested is connected to the number of CPUs that you request. Like, 2 gigabytes per core. So if I ask for, more than 20, the job may fail. Okay, so, but the safe thing to do is not to do anything. It will automatically figure out how much memory that it can allocate. And of course, you can say, send me an email back when the computation is done. Okay. Launch.
Save and launch.
Okay, save and launch. So there are 2 things here, save and launch. Okay, so see this is the latest one, it got launched. Okay, and somehow my name is highlighted. So I think your names will be highlighted, but you're important person.
So how about we move to the next step and see the results?
Result
So we
from
have a run that, yes, go ahead.
Sorry, does this have system size limitation, like the number of atoms that you see?
As many atoms as NAMD supports.
Yeah.
It's just an NAMD run, so it's nothing related. CyberShuttle is conducting your job to the resource. So NAMD is the one running. And also the limitation is the space in your allocation, right? So in CyberShuttle, we have a limited allocation. It's 5 terabytes right now.
CyberShuttle.
This one.
In the space, you mean?
Yeah.
The storage or?
In principle, it's unlimited.
It
Right?
is, yeah, in principle, it is unlimited, and yeah, so you shouldn't worry about it.
Yeah.
The only thing you need to worry about is getting an allocation, like, through access CI or something, or adding your own resource to the gateway. Yeah,
Well,
then,
most of these machines have when you're saving at short storage, right? You're saving scratch, you're saving scratch.
It's being saved from scratch right now.
Like typically, most of the computers have like a 30-day, 60-day, 90-day, pretty big in there.
Or whatever is in your allocation.
so
you can
actually,
do that.
I mean, on many of these machines, there are 2 kinds of spaces, okay? You can run, typically the jobs run in a scratch, but there is also a project space where you can migrate the, data back to, so that they are preserved. I mean, they are not, purged from the scratch. Scratch is always purged because they want to recover that space because large number of people are running. But a project space is very specific to either the user or an allocation. So that, that you can request. I mean, for example, this default allocation that I'm using, I have about 30 terabytes in there. I mean, of course, there's already some data sitting there. So you probably have about maybe 10 terabytes available at this point. Yeah.
Typically, scratch is somewhat limited.
Yeah.
They don't check on that.
Yeah.
Can you just launch Jupyter and VMD, because they might take a minute to load.
Okay, so I'm going, yeah,
Yes.
while he's
In terms of running NAMD
you in the tutorials mentioned about specifying correct flags, right? Like CPU affinity, pinning, etc. Does that automatically happen behind the scenes?
Yes, so based on the type of a job and number of cores that you asked, the CyberShuttle will produce the command line for NAMD for you. And since we work closely with the developers, we're using the command line that is for expense. The command line that is optimized for expense. If you run like a single run or multi-node run, they provide that to us.
But that's one of the greatest things about CyberShuttle for us. Like, if you know what to do in your simulation, the best way possible, that research. If you use your own computer, you're gonna have to tell it what to do. But like for big resources like that, CyberShuttle is using the best that we can compile the software.
For that specific
machine,
for that specific
job.
machine. I don't know if Eric, I wasn't here when Eric was talking, but when he was talking about details of, so the machine has like 100 cores. Core number 0 is for communicating with the CPU.
That's too specific.
No, he was. Core number 1 communicates with the GPU. So when he builds up the NAMD command line, it is defined for that machine. So expense works that way. Maybe another machine works differently. So it goes to that detail.
And yeah, so even if it is not optimized at this point, okay, today, it is easy to, add all those optimizations. So currently, yeah, we did something about the CPU affinity and all those things. But, depending, I think eventually we want to go to a regime where we parse the input and determine even, what it takes. We can come back with some estimates of time. So those many things can be done with these kinds of gateways where we can say, okay, this is what is recommended, okay, to use. Like, for example, if you say 1 GPU for a big million atom system, it may come and say, if you have access to more GPUs, please use that or something like that. Okay, so I'm going to, I selected this Auburn workshop example. I think that previously Diego has run. Just want to make sure that it is actually done. Okay, so this doesn't list all my outputs, but
Oh, yeah, just click on outputs.
Oh, okay.
Yeah, you can see the inputs and the outputs.
Okay. So there are, but it doesn't list all the outputs yet. Okay, so it is doing things. Okay, so we'll still need to improve some of these things. Okay, so in the output section, so there is a standard error and standard out that we can actually see, right? Okay, so there is probably some other.
Oh, yeah, that's the wrong one. Go to the Auburn example on the top. The one that ran for 2 hours.
Which one?
Where is it?
Oh, this one?
Yeah, that one. No, down.
This one.
Yes. Oh.
Okay, let's try that. Okay, so let's see if it is different. Okay, so it has some other coordinates here, coordinate files. So there is a restart coordinates and so on and so forth. It must have been a restart job, is that right? And yeah, so you see there's a pull.dcd. So this is what I was looking for. See, when I said, I want to look at what the outputs are. So now this is better because the previous one didn't have them. Either there was a partial failure or something, or partial run. So now this shows that we have actually a trajectory file available for analysis. Okay. Now, now I am safe, okay, to choose this particular one. Is this one. I'm going to click on VMD. And, okay, so now it is starting a remote VMD process on Expanse where the data is. Okay. Since I am, my hands don't want to be free. I want to click on things. So I want to show some more things. So it is using some kind of an APIs. Okay, so there's an allocation ID. Okay, so it is. So it started a VMD process, and it is exporting the display, through this client. It takes some time to actually establish the whole thing.
It won't be super fast right now because it's running on San Diego for communication. On here, there it's not fast, as you may have noticed. Some of you may have noticed, but
Yeah.
But then it
including-
loads your whole trajectory right now, and then you have a VMP session and do whatever you want.
Okay.
So
This
can
must
you
be
do
that-
something really simple, just put the protein, or
You want to do it?
I can do it.
Yeah.
So I'll just show you that you can do simple tasks on VMD, right on the supercomputer, so graphics. Let's make it quick, right? You will be able to play around later today. So I will just select the protein and show it nicely, but not super nicely. Good. So, I mean, although it's far away from us, it's working pretty decently right now. And we are using right now the basic VNC for remote connection. So we're not using any optimized protocol yet, but we're gonna real soon. Okay, let me put it like this, display as orthographic. And to highlight to you, although it's a steered molecular dynamic simulation, but it's not complete. But what I want to show is that in here, we're pulling this atom, and the enzyme is in the middle, and I will just accelerate. Yes. Oh yeah, you see, it is stretching the enzyme a lot. I'll make it bigger. So it's stretching the peptide, this white thing here. And if I did it well during this 2-hour run, it was able to rupture, but no, it wasn't. But anyway, we don't have to see the whole result. It's a proof of concept. So what I want you to do in the afternoon, if you want, let's run simple analysis using PMD. So I will just run 2 analyses here because I have notebooks for you to test later. The first one will be just at RMSD. So I'm using the RMSD trajectory tool, the one in the middle. And the only important thing about this, that didn't work. So that's on you. So it's not working. It's not updating
So
the
that's-
screen.
Huh? Oh, it is not updating the screen. It should have plotted the RMSD at that point.
It's not opening the plugin. So that's why I uploaded the files, the output files
Ah.
to VMD. Okay, so we'll make it work in the afternoon, right? So the other analysis that we had, because we have the Jupyter notebook for you to run, it was working this morning.
Yeah,
Oh, the hydrogen bonds is opening. I don't know, maybe the window is opening away from you, outside the screen. But anyway, the analysis that we have on the Jupyter notebook is the RMSD. So we just fitted the trajectory, computed the RMSD for the backbone, and the other one is for hydrogen bonds. So the one we put on the notebook is the segment protein and segment peptide. And I'm just getting the unique hydrogen bonds in the end, then write into an output file. And then just run, just like it was in your computer. The difference here is that this file that I'm analyzing is like a few gigabytes, and you don't have to download anything to your computer to visualize and perform analysis. The other thing is that you have PMD, and we have there. Man, San Diego is slow.
Yeah.
So the other functionality, since you have VMD, you can not only run the analysis available on the plugins, you can customize your own analysis. So you can send or type down commands on the TK console and perform the analysis. So since it's not 100% working, I'll just wait and launch the Jupyter notebook. Where is the tab?
Yeah, if you click on this,
Okay, yeah, I want to go back to the tab and open the Jupyter notebook. And just wait for it. Yes. Without increase the size of the screen, right? Say don't disturb. Don't focus, don't disturb. Yeah, so the Jupyter notebook takes quite a while to So let's see if PMD is back. Oh, there you go. So we have the hydrogen bond analysis completed on PMD, but I can say it's ugly. It's ugly. It's using a multiplot right now. Come on, Jupyter. So it's using multiplots, but nowadays everyone uses Python and Jupyter notebooks. So that's where the Jupyter notebook comes.
Wait.
Come on,
Wait.
San Diego. Come on. Yes.
So the PMD is running on the access node, right?
The Jupyter is running in the same node where you ran your simulation.
So
If-
it's not submitted as a job or it's running on the home.
Not the same node, but it could be a different node, but it is sharing the same page, the data.
So it's submitted as a job.
Yes.
Yes, so VMD is a job,
Yeah.
Jupyter is a job, independent.
It's not available.
Yes.
So same for the Jupyter notebook?
Same for the Jupyter notebooks.
Yeah, they can remain, so either you may want to reserve some time for those, or since these are short, I mean, they can use, certain amount of resource. Have to specify that resource as well.
So yeah, how to specify resource for PMD? Because we just.
Yeah, currently it is all in the back, I mean, it's being set, by defined, by default. But I think that can also be opened up.
Suresh has a comment on that.
I think the way we are kind of reviewing is, so multiple options, I guess, these are some things what we need to learn from you guys on what your practical use cases are, because what we are trying, as you can see, the idea is simple right now. If you have a local BMD already installed, you can analyze local data. And then but if you have a large amounts of remote data, you're analyzing it, do you want to, you can run BMD locally there, but maybe you need a big GPU, you should be able to configure to specify that. Or maybe if you have a dedicated GPU cluster where you can run BMD all the time, but use data from everywhere and then log in there. So we are just trying to speculate here all these kind of scenarios. So what this is demonstrations is remote BMD seamlessly bringing the BMC back. And then that one option. So the actual usage will depend upon, I think it'll be good to hear from you guys on what you do on a day-to-day basis and what will help. Like for example, in this Jupyter notebook, let's say I have multiple different environments, like corner environment. How do I switch between them?
The Jupyter notebook right now will run on its own environment. And
Yeah.
if you need to create something else, it's at the beginning of the notebook.
No,
You can install your requirements and create an environment or install all the requirements for your analysis in there. So the Jupyter notebook is running on a default environment, so that we created for CyberShuttle. It has a limited number of packages. But what you can do, even from the Jupyter notebook, you can install new packages. That is the second cell of the Jupyter notebook. I know it's tiny here. Can we improve the size of this? From here?
Yeah, see if we can.
Control plus.
Yeah,
Control
try
Shift
that.
Plus. No, I don't know how to put it. But the point is that if you have a requirements file that you use it to build your environment, you can upload it and just pip install requirements. And then you have your alpha fold or whatever complicated piece of software you need to install in that environment to run your analysis. Every time, right?
Actually, no. So what what we are again, same thing is what both the BMD and Jupyter notebooks and all what we are aspiring to go for. Take the states of what we have done and give you a template approach. If you have a typically used notebook with all your environment loaded, but your data is changing. So then you can have your scripts and everything ready, but data can be changed. Or same thing, if you execute for half of the cells, you can save the state and recreate the next one. And then the other last option, job overwhelming, but last option we are looking at also is, we already have the concept of that is, you can have the notebook locally.
I don't think we can increase the resolution.
Yes,
Can we just?
you can run the computer intensive portion on remote kernel. Right now, if you have a notebook,
Appearance?
you have to have the entire kernel.
Appearance?
running in the same place, right?
There's
So
like
in
a
our group, we
thing.
have modified it so that
Setting.
you can run an agent on the remote machine, just one or two cells can use the computing density on the remote.
Increase.
So all these options are all possible again, but
Text
what we need to
try this
understand
one.
and brainstorm is the use scenario, what is your scenario, and then we can probably advise, okay, this may be a solution, and we can put together that.
Yeah, I
Okay,
mean,
so-
when you launch it, you will see what, there is, for example, in that cell, there's a pip install. So you can install arbitrarily whatever you want, you know, that is available, and it should create your environment. So once you install it, I think it should be there in the container. If you launch the container, it should be.
So.
Some of these things we can look at, but also, you know, for some analysis, the analysis could be a big job, right? It need not be like, you know, interactive kind of analysis. For those things, you should be able to run BMD as an application and then do a long analysis. Yeah, as a separate long job.
So the point here is to show that you can write your own Jupyter notebooks. We can run the script actually needed to run the kernel from the beginning.
Go ahead.
I'll just run all cells. I hope it will work. Actually, click. Yeah, I like to run all. So I'll just run all of them and go back there. So basically, this is just reading your file that you created that we created from the RMSD on VMD and also the hydrogen bonds. While it's running, I will just launch the other notebook because it's taking forever to run. And do the same. So restart and run all cells. Okay, so it started running. Well, at the point, Seaborn is not installed, but we're not using it. Actually, we are for the second notebook.
Yeah, so
Any questions?
maybe like
right now?
some of these advanced ones, maybe we defer to that afternoon session and then go through one by one.
Yeah, since
Just
it's
wanna make
noon.
sure we don't do-
So actually, we wanted to show you to the point that you submit the job and then you visualize with VMD, and then you have the option of the Jupyter notebook. And that gives you flexibility to do whatever you want. And I think that is the point that we wanted to show by now. Based on that.
We skipped, you know, for example, when we uploaded the file, we uploaded some tickle scripts also. You might have seen that, right? For example, mod bcd.pcl. So, I mean, if there is already a known processing, post-processing that is needed on a trajectory file, you can create a script, like a tickle script that you can use, you know, VMD for, and then send it as a post-processing tool, and it can occur, as long as it is in a canonical name. The scripts can pick up and run that right after your NAMD is completed. So, for example, you know, in this case, what we have done is to remove water, to reduce the size, and created a small, just only the protein section of the NAMD trajectory. Or if there are other things that you know that you want to do, you can pre-stage that post-processing and then complete that step as part of the original job itself.
To complete that, so you can also, using the Jupyter notebook, you can edit the scripts that you submitted to your allocation, to your job. So as like I said, that we have one fixed name that's called mod BCD right now. You can put all your analysis TIFO in there. So when a job ends, if it completes successfully, it will run that TIFO script on VMD and perform the analysis. The other option is you open a VMD session to run the analysis there. And then you can upload your own scripts and these things. And in the Jupyter notebook, for instance, you can modify your scripts at will. So in this case, I uploaded on purpose with a different name than the current files we're running there. So this one computes the number of contacts between the two proteins. So one residue, one segment is called prot, the other is called peptide. I put here on the header, and the file name is wrong. So you can just go there and modify struct. And the DCD is called pol. And then you're done. I mean, you just save, and then you can go to VMD and run this script to perform the analysis, and come here later. Well, it's still installed in Seaborn, and come to your notebook and actually do the analysis later. The RNSC, I think it's over. Yeah, so you can go interacting in all cells, see the result of the plots, and all the files will persist in your job when you're done.
Right.
So they will be there. So if you want to download them later, you're good. Here we show the details of H bonds. Well, the evolution of the H bonds while you're pulling a peptide apart. The analysis was also showing the details of which hydrogen bonds had the highest frequency. So you can do your general manipulation of your outputs quite simply. And I guess the Jupyter is done. Okay, so yeah, it failed because I didn't run the PMD script. But you'll have the chance to run it if you use this output file. Shall we adjourn, or you want me to run the VMD? Okay, so we do have time to run the VMD script. All right, so since we waited such a long time to run anything, what is the agent? What is the screen? I'll close the agent and open again, okay?
Yeah, I close it.
Okay, so I'll close and open again to see. Close the Jupyter notebook. Yeah, I have to log in again. I'll log to my account. Right.
Sure.
Okay. So we go to VMD.
Do the contacts from the VMD.
Yeah.
Yes.
How long can we maintain open the VMD station in the Jupyter station?
Yeah, so
That's a good question.
Zahiru, how long is the VMD session open? What is the current setting? Time?
That's not on us, that is on expense. So there's an issue. So if you open your VM, so you launch the VMD session for half an hour, right? The default. Unlimited. But there's only one, we can change that.
Yeah, we can change that. Currently, I think.
Yeah, the only issue that we have that we experience here is that if you do nothing, so if you consume zero of the processor, you're just looking at the different screen, you're running on a supercomputer and doing nothing. So what they do, they kill your job.
If it is idling.
So if it's idle, they will kill it.
But as long as you're using it, I think you can use for half an hour. Right, that's the default time for the VMD run.
Yeah, it could be changed.
Yeah, it could be changed. I mean, currently we're just it's for a starting, but I think all those parameters can be set. We haven't exposed them, but I think we can.
Okay, so let me continue on this since we do have time. So we uploaded the TCL scripts for customized analysis, and the customized analysis is the number of contacts and the pair of the contact pairs along time. So what you can do to do the analysis, you open TK console as I'm opening here, load the file, and let us just run this and hope it will work. If it's blocked, means it's working.
I think the refresh rate is, I think, not as good as.
Okay, well, we're done with number of contacts. So we'll have an output file. So if I list the files that exist here in the folder, it's called number of contacts.dat. Yes, it's here. Okay, next, I'll run another customized analysis that I made, which is the residue pair contacts over time. And yeah, it gives me an error. So this is what I wanted what I showed previously on the notebook. So the name of the file that I'm using, I'm using this script from another simulation, so you can add it on your Jupyter notebook. While the Jupyter notebook is opening, I'll try to change here because it will take a while to open. So then residue pair.pcl. You can edit either from the notebook or from here. And the trajectory is called hold. I'm savvy, I can save it with the same name. Yep. Now run, don't embarrass me. It should take a while. While it's running, the Jupyter notebook is opening. And for you, you won't have a password to type, right? It's their fault. Mine opens normally, right? This 1, 2, 3, 4 password right now. Okay, so while the analysis is running, Jupyter is opening. Do you have any questions for the next 1 minute?
Where is it running, actually?
It's running in San Diego on the Expanse supercomputer. So it is running on the resource where you ran your allocation, your job. So either it was in San Diego or Delta in Illinois, or
Yeah, so
wherever.
the Jupyter.
The files are there,
VMD
so it runs there.
So both the Jupyter and VMD processor are associated with the job. So wherever the job ran, the NAMD job, they will run at the same place and they will use the same data from those simulations. But we need to, it's not automatic for any new resource. We need to make sure that, we use containers for this both VMD and the Jupyter Hub. We need to make sure that those containers are available on the.
Let's wait for it to run all of it. So I'm just running and then I'll show what we're doing here. Okay, Pipin's installing. So if you need a new module, it's installing. Then it's going to load. So what I'm doing here is I'm reading the number of contacts per time. Then I'm applying a signal processing filter. So my signal is softer. Then just reading the file. I want the output to have the time step. So I'm giving the time step because all I have are just data, just the number of contacts per time frame. So I'm adjusting it on Jupyter and hopefully it will plot. Yeah, this is something we need to improve. So I think the Jupyter notebook is just using one machine and one core.
Yeah.
And then it's competing with, it's not the best resource. We should use like 8 cores so you can perform better analysis.
Yeah, I mean, we can resolve the whole 128 cores for that.
Yeah, we should totally maybe make it available to use more cores. And also the storage, because it's taking a long time to get data. Oh, okay. It's coming. So this is the first result that we have in this notebook. So the number of contacts per time, this is a simulation we're pulling apart two proteins. So in the beginning, they have a lot of contacts, and as they separate, you're reducing the number of contacts. Also, there's some things that we do. So we did contacts per residue. So this is just a head of the file showing the contacts, and we do some filtering and fixing of the whatever we do on the output. Actually, we only plot the pairs that occur at each frame, at each given frame. And you will notice from the notebook that we have a fix here. So in order to be able to plot anyway. Then I did like filtering, see the number of contacts per pair. I mean, some actions, but actually within the notebook, it's self-explanatory. I'm plotting the top contacting residues based on the number of contacts they make. And the next one is just timeline. So total number of contacts per pair. So it's really messy. So what you need to do is filter this, whatever you have as a result extra. So I also gave you an example of showing all these contacts in a grid way, so you can, it's easy for you to select which one you want to plot later. Then you can apply your own filtering and pandas to do the analysis. That's what I did for certain contacts. Also seeing like the contacts over time using this scale to visualize. And I only want to visualize a few of them. So there is an example here for you to monitor the contacts of a few of those pairs. And if you go all the way to the end, there is a specific graph for just those contacts that I wanted to analyze. Yeah, and with this one, we're actually showing an example. So in this presentation, we showed CyberShuttle, and then we showed the agent, the CyberShuttle client that works for Linux, Windows, and Mac right away. We showed you how, we gave you a walkthrough the simple interface that we have, showing that you can see your jobs, you can see your projects, you can filter the results in that list based on search engine. You can submit a simulation using different resources. You can put the simulation to a different project, give a description so you can find it later. And you can submit the job to an allocation that can be a default or your own allocation. You can change the number of cores, the number of nodes, and number of GPUs depending on the queue.
So there's one thing that I also want to mention about these allocations. So there is this model called a community allocation. I mean, that's what I use, that's what we are using currently for these runs. So, okay, so one aspect of that is if you want to help your community, okay, you get your funding for the community and provide it for the community. That means that instead of writing a small, tiny little allocation for your own self, you write a bigger allocation request for the community. I mean, for example, you can do it for your lab, small community, or maybe some of your friends and family, like work with a community, maybe the whole region. Think about it, or the whole US, or the whole world. I mean, it depends on how much passion you have for helping your community. So if you can help us, with a community allocation like what we have, you can request I request typically about 10 million core hours per year. Okay, and I have about 300 or so users in one of those gateways. So, if you want to help a whole NAMD community, let's say, I don't know how much time they use. Probably they use I don't know, many millions, hundreds of millions. Maybe not that much, maybe smaller, but that's one way to help. It's like contributing back to the community. Because community is providing so many resources to you, you give back.
I'm just.
Okay, well, just to summarize, after submitting, you are able to see your simulation running remotely, so you don't have to download anything. You can do your analysis remotely using PMD and open a TK console terminal, so you can run specific command line analysis or scripted based analysis if you wish. You can render your movies using, since you have an allocation on a supercomputer, you can render movies. When we enable multi-node for PMD, you will even be able to use PMD across multiple nodes if you have a big animation project or a big analysis like the people from San Diego. And alternatively, we also give you access to a Jupyter notebook. So it will run on your project folder. You have access to your simulation right now, but you will have access to all simulations within a given project or all your projects, right? And then you can perform analysis that go through many experiments at once, not just this small one that we run with one replica.
Yeah, so that I think we need to establish that use case where, let us say you have many experiments in a project, how to analyze all the data from all the projects under that, all the experiments under a given project or multiple projects. I mean, if they are running in the same resource. See, if the data is all sitting there in one place, you should be able to do this, across experiments and so on.
And across resources.
Well, across resources is a little more complicated.
One day.
It's one resource across many.
Yeah. So I think to conclude, this is just the beginning of CyberShuttle. We will bring more features as we have time, and we will try not to break the interface overnight.
Left in the project, so I mean, please. So this is your opportunity to, provide feedback on what is currently there, but also what you want to do, what you want to see, how we can facilitate, what you want to do to make your life slightly easier. Not change the whole life, but it helps a little bit to succeed.
Yes.
Do you have instructions or guidelines for connecting the local app to a local compute resource?
Oh, it's up to you.
Yeah, I think there are some instructions, but we will make them clear. They're probably there. Yeah, typically, so far we have been trying to do this community allocation model where you don't have to worry about getting your time and all. But as we know that NAMD consumes a lot of time, and community allocation is shared by so many people and it may not be enough. So, so one way to do that is to add an allocation. So if you already have an allocation, let us say, there is one mechanism where you can let the gateway as a user on your allocation, and everything will be taken care of. So you go through the gateway, and you will use your allocation, but everything is automatic at that point. If you want to add your own allocation and your own way to process and so on and so forth, so there is some additional steps. But if you have your own resource to define, for example, here only some national resources are defined. Let us say you have your campus cluster. It can be added here, and it is reserved only for your jobs. You don't have to let other people use that local resource. So we can do that too. So that means that we need to register your local resource as a resource that is available through the gateway, and make sure that you are the only one authorized to touch that resource. So I mean, we need to create some clear documentation about it, and we'll do that. There is some documentation, and we know how to do it, but I think it's maybe that's a point.
So another point on that. On sharing and seeing the results. If you're the PI for a project, you can see what your students are doing. So you have.
Well, no, if the student is willing to share.
Yeah, it'd be useful for you. You can control the allocation, see who's running what.
If they want to graduate, just share. That's how.
All right.
That's it.
No, I think, just to be clear on one point, yeah,
Yeah,
I think you have nicely summarizing all those future points. So on the local app to local resource, like, I just want to say that, there is it goes through the gateway. So gateway is a centralized resource. And as Sudhakar was trying to explain, there are a lot of access controls where you can bring your tools, bring your resources, and then controlly enable that to yourself or to your group on who to use. And then that connects the from web interface, you see all of that. So the local app also connects to the web platform. So just want to be clear that it's not like everything in a university, it's running a central platform. You add your local resource to the platform and your local app now can I use through that broker through this central platform, or same likewise. So basically you can imagine the platform is connecting to national resources, your local resources, and then you can use it from a web browser and then a local app.
So this is an Electron client, which is a local application. You can usually plug in other applications or automatically associate some data that is in the gateway to another local desktop application, for example, Excel spreadsheet or something like that. So those things can be easily managed through that this desktop application.